Hello everyone, and welcome back to the MGPUSim tutorial. Now we are going to talk about the design philosophies behind the development of our Akita framework. Our first design philosophy is that all information in the simulator cannot flow from one component to another magically. If we use magic, one component can access directly the data of another component, that is, by means of class fit access or getter-setter calls. This, of course, introduces simulation inaccuracy as it is not possible to model the particular communication overhead. Also, it breaks down encapsulation and compromises software modularity. However, there are certain cases where the usage of magic is recommended, as we will explain in our discussion part of the tutorial. Our second design philosophy is that simulators should track data with timing, that is, simulators should utilize real data values in the simulator, rather than allowing the emulator to magically access the data. Separating data flow and time calculations hides errors in system design, making value-dependent modeling difficult. Our third design philosophy is that simulators should avoid busy ticking. There are two major sources of busy ticking in simulators. The first type of busy ticking happens in cycle-based simulations that tend to visit each model component to update the state at every cycle, even if such updates are not required. We should avoid unnecessary state updates to maximize performance. Akita framework achieves this by using an event-driven simulation engine. That is, in Akita, a DRAM controller can calculate that a request takes 300 clock cycles to complete when the request arrives. Then nothing needs to be modeled in detail during the 300 clock cycles. So the DRAM controller can schedule an event in the event-driven simulation engine after 300 clock cycles and skips state updates until then. The second type of busy ticking is caused by components that repeatedly try to send data as shown on this diagram. Since a component has no information about when a connected connection becomes available, the component has to retry each cycle. To avoid this type of busy ticking, as explained in the previous video, we allow the connections to explicitly notify connected components when the connection is available. Therefore, a component can avoid updating the state if all the outgoing connections are busy, and update its state after a connection is available. Our fourth and last design philosophy is that we should simulate parallel hardware in parallel. Digital circuits run in parallel. As we can see, in a GPU or multi-core system, the group of components on the left, that is core and cache, run independently from the group on the right. They are usually driven by the same clock signal. At a clock edge, they cannot communicate with each other. Since these two state machines do not communicate at a particular clock edge, nothing prevents us from running the simulation of the clock edge in parallel. As explained in our first video, MGPUSim has inbuilt support for multi-threaded simulation that can be activated by the user in order to take advantage of this natural parallelism present in digital circuits to achieve faster simulations. In our ESCAP application of MGPUSim, we analyzed the number of events that happens at the same clock cycle for the AES benchmark. As we can see in the figure, overall, this number of events varies between 60 and 100 for most of the time, providing sufficient parallelism to keep a 4 to 8 core system busy. Thank you very much for your attention. Please don't miss our next set of videos devoted to MGPUSim. Bye-bye for now.